In this video, we'll look at two techniques for solving first-order linear differential equations, although we'll also look at second order briefly. And the first one is kind of a simple one called sometimes guessing or guessing the form of an equation. It's not very mathematically satisfying, but it is sometimes a quick way to get at a solution. And then the second one is more systematic, and it's called the method of integrating factors. So let's take a look at how these methods work. First, for guessing the form, we'll begin with a fairly simple differential equation. So y prime is equal to 5 times y. If we try to guess the solution here, we might be reminded of something we looked at previously. If we just had y prime equals y, then we know that y of t is equal to e to the t works as a solution. But if we put y is equal to 5 times y prime is equal to 5 times y, all of a sudden this is no longer a solution, and we could check. On the left-hand side, if we take the derivative of e to the t, we would get e to the t. On the right-hand side, we're hoping this works. We would get, so this is the y prime here. On the right-hand side, we would get 5 times e to the t, and of course, e to the t is not equal to 5 times e to the t, so that doesn't work. This is the wrong guess. But we could try a different guess. One I sometimes see people try is this, but you can check pretty quickly that 5 times e to the t is also not a solution. You would just get something like 5 e to the t, because that's derivative of 5 e to the t. And on the right, you would get 5 times 5 e to the t, which is 25 e to the t. And so this also is not the correct guess. But if we take a step back and remember the chain rule, we might know that if we put a 5 here, this will work. So then we would have something like y prime is equal to 5 e to the 5t, which is equal to 5. And then we have an e to the t here, so that's just a y. Of course, any other constant out here would also work, and I'll let you check that on your own. But this is just an example to get us started. So let's say that we didn't want to be quite so clever. I had to kind of in advance come up with a 5 here, just by sort of, in some sense, just looking at it and using my familiarity with how equations work, that kind of thing. In this case, it's a little bit of intuition to get there. Can we get something which uses a little less intuition? And so let's take a look at that. If we did something like y prime, again, let's look at y prime is equal to 5y, and maybe we would know that this is something like an exponential, but maybe we were being a little bit cautious. We don't know what the constant up there is. Actually, I'm going to put a c here and an r there, where r, actually, maybe we'll leave the c off for a minute, but where r is to be determined. And this might seem a little bit silly because we just saw that r equals 5 works, but maybe there's another value of r that works, or maybe we will be able to generalize this to other settings. So let's see. So this is our guess. Is y of t is equal to e to the rt. And we can just check it. As I said, this is a little bit mathematically unsatisfying because we're just sort of using guess and check like in elementary school. Oops. So y prime is r e to the rt. But what we would need is, so substitute this in, right? We would have substituting. We would get on the left-hand side, right? We have y prime is equal to 5y there. So we'd have r e to the rt. That's our y prime. And on the right-hand side, we would have 5. And then we're just plugging in y itself, so e to the rt there. And if you want, you can divide through by e to the rt, which is never 0. Or just compare. In either case, you get r is equal to 5. So y of t is equal to e to the 5t is a solution. Okay. Nothing too earth-shattering there. let's take it up one notch, and this is about first order equations, but I want to get the kind of guessing technique across a little bit. So let's consider something like y double prime is equal to 5 times y. So this is a second order linear equation, constant coefficients here. Excuse me, I want a negative 5y. It might not be immediately obvious what the solution to this equation is. Now, we could guess that it's e to the RT like before, and this would be okay. For now, I'm going to make a different guess just to illustrate the point. So if you think about functions whose second derivatives are themselves, are, say, negative themselves, like forgetting about the 5 for a minute, if we just had y double prime is equal to negative y, then one possibility here would be something like sine of t. But with a 5, it's maybe a little less clear what that would be like. And we know if we try to do something like put a constant out in front here, this is just a multiplier and it won't change anything in this linear equation. So thinking about the chain rule again, you can put an r on the inside. And let's see how this works. So then we need, so this is our guess. And we'll check it. And so to do that, I need a table. It's just, so we have y here. Y prime will then be, well, the derivative of sine is cosine, rt, but then I have to use the chain rule to multiply on the inside. We multiply by the derivative of the inside, so we get r. And then y double prime, the derivative of cosine is minus sine, so minus sine of rt. We already had an r from before, but when we use the chain rule again, we get another r coming out. So it's you get a minus r squared there. And then we can plug this in. So we're plugging it in again into the equation. So we get on the left-hand side minus r squared sine of rt. That's y double prime. And on the right-hand side, we get minus 5 sine of rt. And so the only way that these two functions can be equal for every value of t is, of course, there are some values of t that make sine of rt equal to 0. But we'll just choose a value of t that doesn't make sine of rt equal to 0, in which case we can get, so that implies that r squared is equal to 5. And then that tells us that r can be plus or minus square root of 5. Sine is an odd function, so we could bring that minus out and just absorb it into a constant in front. So for example, y of t, right? So for example, y of t is equal to sine of the square root of 5 times t is a solution. Of course, we should maybe double check that we didn't introduce any additional solutions by taking this and plugging it into the original equation. But there we have, I'll leave you to do that on your own. And there's a solution, which I think is maybe not immediately obvious from this thing. It maybe wasn't immediately obvious that it should be a square root of 5 there. If you saw that, great. But this is how to do it for this thing. I encourage you to try it with the guess we tried before of e to the rt. Does that work? Maybe r doesn't need to be a real number in that case. But I'll leave us. We'll explore things like that down the road, but I'll leave it alone for now. Another interesting thing to try here would be to try something like, oh, what if you tried, so cosine of RT also works. You can give that a try if you want to try it out. But if you try something like a tangent of RT, this will fail. And this is a pretty nice one to try. It involves taking some derivatives of the tangent function, which might not be so nice, but give it a try and see what happens if you're curious about that. So that's sort of the method of guessing solutions. I want to show you one more for a second order equation, which gives us something that I think is a little less obvious. So last time we looked at the following equation, y prime plus 5, y double prime plus 5y plus 6y, excuse me, y double prime plus 5y prime plus 6y equals 0. And let's make a guess. And without being too clever, let's just reuse our previous guess for the problem a little while ago, which is e to the RT in this case. So I guess we're checking this thing. Y prime is equal to R e to the RT. And now we need Y double prime to be R squared e to the RT, using the chain rule again. And we plug in. So we would have something like R squared Y double prime plus 5R. Excuse me. We would have plugging in the Y double prime to this spot of the equation. This is R squared e to the RT. Then plus 5 R e to the RT. We'll put parentheses so you can see what's being plugged in. Plus 6 e to the RT. And that all is equal to 0. We're setting it equal to 0 because we are assuming that this is a solution. Now, if we get something like that R has to be non-constant, we would be in trouble. But in this case, let's see what happens. So we can rewrite this. Notice that everything has a common factor of e to the RT. And so we get something like R squared plus 5R plus 6 times e to the RT is equal to 0. But e to the RT can never be 0. So the other factor must be 0. So R squared plus 5R plus 6 is equal to 0. And now this is a problem of basic algebra, right? We can factor this. So if we put an R and an R there, we know that 6 has factors of 2 and 3. And if I put a plus in the middle, we get something like that, which tells us that R should be -2 or -3. Okay, so we've got some values of R that seem to work. Let's try these out. So this means that Y of t equals e to the -2t is a solution. Maybe we'll call it Y1. And so is Y2 of t. And last time we verified that these are solutions. So the Y1 and Y2 here just designate like first solution, second solution, and it doesn't matter the order. I mean, so long as we agree on it beforehand, you know, somebody else might call this this one Y1, the other one Y2. It doesn't matter. It's just that we have two distinct solutions there. And we saw earlier that if you had, in the previous video, we saw that if you have two solutions to this equation, you can add them together with constant coefficients. So let's just note that and get another solution. C1 e to the -2t plus C2 e to the -3t is also a solution for any constants C1 and C2. Any constants at all there, we'll make that a solution. Okay, so this is a kind of nice illustration, I think, of the guessing concept. It takes it a little beyond the just obvious, guessing the solution is e to the 5t here. We're sort of guessing that there's a form, we have some intuition or a hunch, or maybe we don't have any other ideas, and we just plug this in and see what happens. Let's take a look at when this goes wrong. When can this go wrong? So let's see an example. This is something called an Euler equation. If we have something like t squared y double prime plus 5t y prime plus 6y is equal to 0. So I've got a similar looking equation there, but now we have these non-constant coefficients. Non-constant coefficients. So this is, of course, this is linear second order. Okay, but non-constant coefficients. So let's try y of t is equal to e to the RT. And just to be clear, so that maybe seems like a good guess, but this will fail. So it turns out e to the RT always works when you have a linear equation with constant coefficients. even works for higher order, and let's say homogeneous equation. But for the non-constant coefficient equation, well, let's see what goes wrong. So then, once we have this guess, the rest of the problem, we're in lockstep. We have no more choices to make at this point. So y prime will be e to the rt, y double prime is r squared e to the rt, and we plug in. And what do we get? So trying to get that on the screen there, we'll get something like t squared times r squared e to the rt plus, so that's from the first bit, maybe I'll put it here, 5t times y prime, which was r e to the rt, and then plus 6 e to the rt, and that's all supposed to equal 0. We hope it equals 0, right? Solving this, so we can get t squared r squared plus 5tr plus 6, and factor out an e to the rt equals 0. And now we, again, if this thing is equal to 0, well, e to the rt is never equal to 0. So you can either think of dividing by e to the rt, or just thinking about when you have a product of two things that equals 0 and one of them is not 0, the other one must be 0. So we have t squared r squared plus 5tr plus 6 is equal to 0. And now we can solve. Remember, we're trying to solve for r. So, well, this one looks a little more complicated to solve for r. It's not in exactly the form that we saw before. You could be a little bit tricky here and solve this. Think about this as a quadratic equation in the variable t times r. But I'll just be simple and use the quadratic equation. If I don't know how to solve something quickly, I can just try the quadratic equation. So here, r is minus 5t plus or minus the square root of b squared, which is 25t squared, that's this thing squared, minus 4 times, well, 4ac, so it's going to be minus 4 times t squared times 6. So 4 times 6 is 24, so it's minus 24 t squared here, and then divided by 2a, so 2 times t squared. So if we have something like this, well, something kind of nice seems to happen up here. We get a 25t squared minus 24t squared. So we get something there like negative 5t plus or minus. Then it's just a t squared there. So the square root of t squared, if we want to be careful, we can write that as absolute value of t divided by t squared here. But this thing turns into, of course, well, this thing turns into negative 5 halves divided by t plus or minus then t divided by t squared. And the problem with this is that this expression here is not constant. And our whole assumption when we started taking derivatives, so this guy is not constant. And this is a big problem because when we were taking these derivatives up here, in order to be able to perform this step, we were assuming that r is constant there. Otherwise, we would have to use some other rule. These steps here would be wrong to begin with. So I can't just guess that the solution, the same technique doesn't work on the same problem, right? It's a very similar looking problem, but with those t squareds, it's a very different problem. So I won't say too much about solving this, but note you can try y of t is equal, instead of, so we guessed e to the rt with the t upstairs in the exponent, and we just saw that that doesn't work. So it turns out that if you guess t downstairs, that this will work for certain values of for certain values of r. You can try this. I'll let you try that on your own if you want to see how this works. The solution might not be especially pretty, but This is one way to do it. Now, that doesn't mean that there's always going to be a way to do it. For instance, if I change the original problem, instead of a 2 here, I have a 3. There's not really a good way to approach this problem that I'm aware of. Maybe this particular one has a nice form somehow that somebody can spot or that somebody's discovered, but this doesn't really fit into the standard classification. T to the R, I believe, will not work for this problem. So it's a very special form of problem. And in this case, this is what's called an Euler problem, where the power out in front matches the number of derivatives. So here's a power 1 and a first order derivative, power 0 and a 0th order derivative. If it's of that form, T to the R tends to work. If it's not, there's not necessarily a great solution. Just like in this case that we looked at before, if we have constant coefficients, e to the RT is a good guess. Okay, so that's some of the idea of guessing a solution. Let's take a look at the next technique, which is called integrating factors. And this is more systematic. This is also something that comes up again and again and again. Sometimes at the highest levels of research, it can be adapted to numerical algorithms for solving differential equations. It's an incredibly powerful technique that I think is sometimes overlooked a little bit. But let's take a look at this technique. So I want to introduce this by building it up from kind of a simple idea and making that idea more and more complicated with each step. So let's take a look. So first, let's intro. Let's solve y prime is equal to 5. I think you can do this. If we have y prime is equal to 5, then we get y prime. Then we can just integrate both sides with calculus, right? We get y is equal to 5t plus a constant. That's it, right? Done. Okay. So if we had a differential equation in this form, we can solve it quickly. So let's say, let's call this intro 1. Intro 2. Let's make the problem a little more complicated. Something prime is equal to 5. And the something that I want to put here is t times y. So all of a sudden, we have an equation which is no longer autonomous. The coefficients are not constant. It is still linear. And it's in a nice form. In fact, it's pretty much the same form as what we had before. It's just that there's instead of a y, we have a ty there. So if I just sort of think about this as some type of blob prime equals 5, I can solve for blob in exactly the same way as I did before, like this. So applies as before. Ty, it's equal to 5t plus c. And this means that y, now I can solve for y. Y is equal to 5t plus c divided by t, or if you like, that's 5 plus c divided by t. It's a pretty common mistake, by the way, to say, well, c is just any constant, so instead of writing c divided by t, I'll write that as a c. But that is a mistake. Here, as t goes to 0, this expression goes to infinity, for instance, or minus infinity, depending on the sign of c. Also, when we're done with the problem, a lot of times we'll restore the of t part of the solution. So there we have it. Y of t is equal to 5 plus c over t, making sure not to simplify, which would be, not a simplification would be wrong, not to simplify this to just a general constant. Okay, so hopefully that wasn't too bad. We solved this equation, and then we solved this equation by essentially the same technique, except for just dividing at the end. Okay, let's take a look at introductory problem 3. Let's solve this problem. Y prime plus, ty prime plus y, it's equal to 5. All of a sudden, this looks like a significantly more complicated problem. We can't just integrate anymore. So for instance, if we tried to integrate, we don't have this thing by itself. So it's not even clear what could happen there. Maybe we could do something like try to get rid of this t, divide by t. Maybe we could try something like that, but it's far from clear what to do, right? Because we would still have a y over here, and we don't know what y is. We can't just integrate the equation. So on the other hand, notice that ty prime plus y, this didn't come from nowhere. This actually is just the expression we had before. It's ty prime, and it's by the chain rule. Let's double check that. Oh, sorry, not the chain rule, the product rule. Excuse me. If I take the derivative of t, I get a 1, and I leave that alone. I leave the y alone, so I get just y there. On the other hand, if I take the derivative of y, I get y prime, and I leave the t alone. So this is just the product rule showing up. So this intro problem 2 and intro problem 3 are the same, just written in a slightly different form. So ty prime is equal to 5 from the equation. And then we get, just as before, all right, as before, we get that y of t is equal to 5 plus c over t. Okay, so you might think that I'm pulling a fast one on you here because we seem to keep solving essentially the same problem over and over again. But in just a moment, we'll develop this into a pretty nice general technique. Okay, so we've got same problem technique. This was the same problem as problem 2, just written in a different form. Okay, let's look at intro problem 4. And I'll change it up on you just a little bit. Let's do something like y prime plus, say, 2 over t times y is equal to 3 over t squared. Let's just do, 3 over t squared. Okay, let's give this one a try. Now, I'm going to do something which seems like it comes out of the blue, and then I'll teach you how to do this magical step. So the magic step, which will not be magic in a minute, we'll see how to do it. Magic step is going to be to multiply by t squared. It doesn't have, by the way, anything to do with this t squared down here, but let's multiply by t squared. So then we get t squared y prime plus 2, well, 2 over t times, so let me write it like this, t squared times 2 over t, y equals 3. That's why I chose the t squared, is because when we multiply, it just turns out to be something nice over here. It's not so clear why we chose the t squared, though. So, of course, this square cancels with 1t on the bottom, so we get t squared y prime plus 2t y is equal to 3. And this might seem pretty disconnected from the previous problem. However, notice again, by the product rule, we have, well, take a look. Here we have y, the derivative of y, and here we have y by itself. Here we have t squared by itself, and over here, we have the derivative of t squared. So the product rule applied to t squared y is t squared y, right? T squared y prime. So take the derivative of the second one, for instance, plus 2t y. Here, this is t squared prime. So by the product rule, this on the left-hand side is what's called a total derivative. That is, it's just a derivative of a function, ty squared. Remember that y is unknown. It's an unknown function of t here. We can't do much with it at this point. But we can do something with t squared y. T squared y prime, it's equal to 3. So we're basically using the product rule on the left-hand side in reverse. That's the technique of integrating factor. It's kind of going backwards from product rule. Now it reduces to what we've seen before. T squared y is equal to, now I integrate to 3, so I get 3t plus a constant. And then we can solve for y. So y of t, I could just write y, but it's nice to write y of t sometimes, is, well, let's see, we divide by, so we get 3t plus c divided by t squared, which you could write as 3 over t plus c over t squared. That's our answer for this problem. Okay, this is the technique of integrating factor. I now have to teach you how to find this special multiplying factor, the special thing that shows up there. That's why it's called an integrating factor, by the way. It's so t squared in this case is the integrating factor. So let's take a look at the technique in general. Integrating factors in general. In fact, you can make it more general than this, but this will be good enough for our purposes. So if we, the standard setup is, so let's look at the setup, because again, problem form is very important. So the setup is something like this: y prime plus p of t times y is equal to some f of t, where p of t is, purely a function of t. If you had, for instance, some other function over here, like some a of t or something like that, if this function was non-zero, you could divide through. In fact, even if it had some zeros, it often will work to divide through and then just call the new thing in front of y p of t. So in this case, we have p of t. So for instance, in the last problem, our p of t there would be this 2 over t, and the right-hand side, the f would be 3 over t squared. So we have something of this form. If it's something with a second derivative, the integrating factor technique doesn't really apply here. There's certain things you can sometimes do using something called a matrix exponential that kind of works, but in this case, we're really just looking at things in this form. If it was nonlinear, something like that, so y squared there, the integrating factor technique does not apply. It only applies to first order linear equations, and in particular when you put them in this form. So the idea is to multiply by some function, and it's often written as the Greek letter mu of t, mu. So multiply by some function mu of t, because I guess for multiplier, to be determined. So we don't know what this function is going to be. Such that we can use the product rule in reverse. So that's the idea. We saw it kind of work with this magical technique there of multiplying by t squared. So in that case, our mu function would be just t squared, and it worked perfectly. So let's try it. So we have something like this: y prime plus p of t. Let me leave some room. P of t, y equals f of t. Of course, y also depends on t, but I'll leave it off of there so we don't clutter things up too much. And then I'm going to multiply through by mu of t. I mean, I'm allowed to multiply both sides of the equation by the same thing. Now, to use the integrating factor technique in reverse, what I would need is, let's see, here we have y, derivative of y, and then y left alone. So what would be nice is if here, so here I have mu, and what would be nice is if this thing was the derivative of mu. So what we want this to be mu prime. If we can get that thing to be mu prime, we would have mu times y prime plus mu prime times y. We can use the product rule in reverse, just integrate both sides and solve. So how can we get it? Well, we'll just choose mu in that way. So want to choose mu so that mu of t, so that mu prime is equal to p of t times mu, like that. That would do the job, right? So the question is, can we find a function which works like that? And if you think about it, it's not all that bad to find something like this. For instance, if p was just a 1, then mu prime, we would want to choose mu such that mu prime equals mu. In that case, we could just choose mu to be e to the t. If we had a 5 here, we would say we could choose mu equals e to the 5t would work. If we just have a general function here, maybe the exponential trick would work by the chain rule, but what would have to happen is we would have to take a derivative of what's in the exponent. So to do that, we'll just choose mu of t to be mu of t equals e to the integral of p of t dt. And so this integral up here is an antiderivative. Right? So then we would have mu prime would be, well, the derivative of an exponential is just the exponential. So it's just that exponential times the derivative of the argument, right? Which the derivative of an integral by fundamental theorem of calculus or by the definition of antiderivative just gives you back the function itself. So I'm writing, right, this thing is just p of t. I'm using that right there. And so this bit here, this is our mu. So indeed, this is just p of t times mu. So that's it. That is the magic. That's how choosing mu in this way is the secret sauce to make the integrating factor technique work. And just to be very clear, so it's e to the integral of this factor, the factor that's in front of y. So if I have a 7 or something here, well, I better divide through by that 7 to get the integrating factor technique to work. If I've seen sometimes students make a mistake of choosing whatever coefficient is in front of the y or somehow involving the f, it really only works in one way. That is, you're going to pick the integrating factor to be e to the integral of the term, e to the integral of the coefficient in front of y. So let's see how this works in practice. So first of all, let's see that we did use it a minute ago. So this magic step, here we had y prime plus 2 over ty equals 3 over t squared. So let's look at that again. Y prime plus 2 over ty is equal to 3 over t squared. And then we'll choose the integrating factor. So integrating factor, we choose to be e to the integral of 2 over t dt, like that. All right, well, what is the integral of 2 over t? We just want an antiderivative here. So that's natural log of t. Now, it's natural log, 2 times natural log of t. Notice that more precisely, we should have an absolute value here. But that absolute value will just turn into a plus or minus. We just want some particular integrating factor. So either choice will work. And in this case, we'll just choose the positive one. Also, there should be a plus c for a normal antiderivative. But again, in this case, we just want some integrating factor. So this is one case in mathematics where you can leave off the plus c where you do an integral. It won't change anything. In fact, it makes it look a little messier. So let's just cancel the e and the log to get 2t, correct? Careful, that's not correct. You can't cancel those. If you do, you don't get the right thing. It's not correct. We can't just cancel it this way. We need to rewrite this in the form, for instance, e to the natural log of t squared. And now, since we have e to a pure logarithm with the same base, we can cancel those, and we get that this is t squared. Okay, so just be a little bit careful there. I've seen that mistake happen many times. Even PhD students I've seen make that mistake. Okay, so integrating factor here is just t squared. Okay, now let's that's so and proceed as before. So we saw that a minute ago. Oops. Right. So we multiplied by the t squared, and we cranked through the problem and integrated. Okay. Maybe we'll see one more example. This integrating factor technique. So yeah, let's try this one. So y prime plus 1 over, actually, let's do something like, say, yeah, 1 plus t squared y prime, it's t squared y prime, plus y equals the arctangent of t. Let's try something like that. Actually, you know what? I'm going to make this maybe just a little bit simpler. Let's put just let's just put a 3 over here for now. All right. Then in this case, if we let's see, yeah, we'll keep a 3 over there. Let's see how that goes. So okay, if we I'm sorry, let me put a 3 times 1 plus t squared. There we go. Excuse me. Just to illustrate the technique. So first of all, let's note that this is not in the form, in the integrating factor form. We need something of the form y prime plus p of t y equals some function on the right-hand side. We need there to be a 1 in front of this coefficient. Well, we can divide through by 1 plus t squared to get that. So we'll have something like y prime plus 1 over 1 plus t squared y, and then that's just equal to 3. Okay. This means that our integrating factor will be mu of t. It's equal to e to the integral of 1 over 1 plus t squared dt. And e to that, the integral up here, this is e to the, well, the integral of 1 over 1 plus t squared is the arctangent of t. And so tangent of t there. So we can multiply through, and this looks a little bit nasty, but it'll work just fine. So we get here something like e to the arctangent of t times y prime plus, and then it's going to be e to the arctangent of t times 1 over 1 plus t squared y. It's equal to 3 times e to the arctangent of t. Okay, this looks like something which is a little bit nasty, but let's take another step. We know from our construction, well, right here, this is the derivative of arctangent. So we can rewrite this as e to the arctangent of t times y prime. That's this whole left-hand side. It's collapsing into this nice expression. And then that's equal to 3e to the arctangent of t. Okay, another step. Now we just have to integrate both sides. Now it turns out that this function on the right does not have a nice antiderivative. At least it's not one that I'm familiar with, but that is all right. if we integrate both sides, we get e to the arctangent of y is equal to 3 times the integral of e to the arctangent of t dt. And dividing through, we get 3 over e to the arctan t times the integral of e to the arctan of t dt. Now, this might seem like a little bit of an unsatisfactory solution because we're left with this nasty integral behind. But from the perspective of differential equations, we normally count this as a solution. That is, we've completely untangled y. We might, for instance, use a numerical integration technique. If we wanted an exact solution or we wanted to plot this or something, we might use an numerical integration technique to approximately compute this integral. We could then take a look at the graph or something like that. But from the perspective of differential equations, there's nothing left to solve here. This is a complete solution. It just happens to involve a function which is rather nasty. Notice if you have something, for instance, the same kind of thing happens in Calc 3. If you want to integrate e to the t squared, there's no nice closed form for this. The best you can really say here is that y of t is the integral of e to the t squared dt. That's it. There's no further simplification that can be done to integrate this function. So sometimes in differential equations, and even in Calc 2, we have to get used to this idea of leaving functions in a form involving an integral somehow. But that's how the integrating factor technique works. I want to do just one last pass to kind of show you how this thing works in general. So if we have, general solution. So let's say we have some type of abstract differential equation, y prime plus p of t y. It's equal to f of t. So it's not a completely general differential equation. It's a first order linear equation in this particular form. But then multiply by mu, where mu prime is equal to p times mu, p of t times mu. So we get mu times y prime plus mu p y. I'll just leave off all the of t's for now. And then mu f, just multiplying through. We know that this left-hand side, we've seen this many times, this collapses to mu times y prime. It's equal to mu of f. And then we can integrate. So mu of t, put back the of t's now, y of t is equal to the integral of mu of t, f of t, dt. And so the general solution to this kind of equation is y of t is 1 over mu of t times the integral of mu of t, f of t. Or if you want to write down what mu actually is, this is 1 over e to the integral of p of t dt. The integral of e to the integral p of t dt, times f of t dt. That's our general solution to this first order equation. So we've solved a whole class of equations, at least up to an integral. And this is fairly nice technique. The integrating factor technique is a pretty powerful one. There are many examples on the worksheet for you to practice this integrating factor technique. Once you master it, once you try, 5-10 examples, I think you'll have it down, no problem. So thanks for your attention and have a great day.